Okay, so in this section, we're going to be looking at applications of right triangle trigonometry. And in order to do so, we first need to have an introduction to inverse trig functions. All right, and previously I gave the distinction between reciprocal and inverse. All right, so let's maybe go into just a little more depth on what we mean by inverse trig functions. So the concept with inverse trig functions is the same principle as inverse functions that were covered earlier in chapter 1. So remember the relationship between functions and inverse functions with respect to their domains and ranges. So notice that we put a -1, which kind of looks like an exponent, but it's an exponent that looks like it's on the letter F or whatever letter we use to represent the function. This is not to indicate a reciprocal, but to indicate an inverse. So, if we have a function f has its own domain and range. So I use d sub f and r sub f to represent the domain and range of that function f. And so the domain constitutes all of the inputs of f that then f maps to outputs in the range. Now, when we go through the process of taking f and finding its inverse, this inverse function that we find takes the outputs of f, and those outputs of f now become inputs for the inverse function. And what was once the range of f now becomes the domain of our inverse function. And so as a value from the range of f goes into our inverse function, what comes out of the inverse function is an element of the domain of f. So this is what it means for two functions to be inverses of each other. And over here, this is more of an abstract example. Over to the right, I have a more concrete example. So here our function is 2x. And so if we put 3 into our function, then 3 times 2 gives us 6. So you can see that 3 is in the domain of f and 6 is in the range of f. Now, in order to find the inverse of f, what you do is you swap x and y, and then you solve for y again. Okay, and that's where the inverse of f equaling 1/2 x comes into play. So this is finding the inverse. All right, so with this inverse function, we can plug 6 into our inverse function here, and 1/2 of 6 is 3. So you can see that the domain of the inverse function is the range of the function, and the range of the inverse function is the domain of the function. Okay, that's the relationship between the two of them. Now this right here is just a review of inverse functions from chapter 1. Now in the trig functions, they too are functions, and they also have inverses. So what does that look like? So the input, so we'll look at cosine first. So cosine as a function has theta, or an angle measure, as an input, such as 30 degrees. And so when we calculate the cosine of 30 degrees, what we get out is some value on the x-axis. We get the square root of 3 over 2. So this is the domain of cosine, and this is the range of cosine. Now, when we use an inverse cosine function, the inverse cosine function takes a value of x and it outputs the angle. And there's different ways to represent inverse cosine. The more traditional way, that maybe is more consistent with what you saw in chapter 1 is we have cosine with the -1 next to the word cos or cosine. But other textbooks, other sources, they don't use that -1, possibly because of the confusion with reciprocal. And so they use arc cosine instead. And sometimes you'll even see it with an a cosine. Both arc cosine and a cosine, those mean inverse cosine. Okay, so there's 3 different ways you might see inverse cosine kind of in the wild. And the same relationship holds with sine and tangent, right? So if you take 30 degrees and you calculate the sine of 30 degrees, then the output is going to be a value on the y-axis, which is 1/2. And if we take the inverse sine of 1/2, that'll get us back to 30 degrees. And again, inverse sine can be written as arc sine or a sine. And the same is true with tangent. If we take 30 degrees as an input and we calculate the tangent of 30 degrees, that gives us the ratio of y over x. I think I need to change that to the square root of 3 over 3. And if we do the inverse tangent of square root of 3 over 3, then we get 30 degrees. And again, we can write inverse tangent with what looks like a -1 exponent there next to the word tan, or we can write it as arctangent or a tangent. Now, this is more, of an abstract way of thinking about it. But remember that cosine, sine, and tangent, these relate specifically to right triangle ratios. So how would this look like both a trig function and its inverse when written around a right triangle? So here we've got triangle ABC with our angle of interest being 30 degrees. If we take the cosine of 30 degrees, that gives us the square root of 3 over 2, which is the length of side AC. And if we instead had the length of side AC and we do the inverse cosine of that, that would tell us that our angle of interest is 30 degrees. It goes the other way. Now with sine, if our angle of interest was 30 degrees, right, SOHCAHTOA, so that would be opposite over hypotenuse, but the hypotenuse is 1. So if we take the sine of 30 degrees, that tells us that the length of side BC, that's the opposite side, is 1/2. But instead, if we knew that the length of the opposite side was 1/2, we could take the inverse sine of 1/2, and that would tell us what our angle of interest is. it goes the other way. And with tangent, if our angle of interest was 30 degrees, and we take the tangent of 30 degrees, that gives us the slope of the hypotenuse. And coincidentally, if we had the slope of the hypotenuse, we could then apply an inverse tangent to it, and that would tell us that our angle of interest is 30 degrees. So this basic concept here, is a huge concept which applies to a multitude of different disciplines. And so the details of these inverse trig functions are going to be covered in more depth later, but a simple understanding of their existence and use is quite powerful. So a normal trig function takes theta as an angle as a given, and it allows you to calculate, an x direction, a y direction length, or a ratio of y to x. But an inverse trig function does the opposite. It takes in the length of a right triangle side or ratio and outputs an angle inside the right triangle. So it's kind of like it's an inverse relationship. Okay, so I think that is as much as can be explained. Now it needs to be shown. Let me know if you have any questions.